Swayam Prabha. Digital India. Educated India.
Resonance. Does that resonate with you? We are going to see what that means. Okay, resonance is when you have a lot of correct Lewis structures for the same compound. So let's look at, that's just the definition. So multiple correct Lewis structures for the same molecule. What does that mean? For example, let's take a molecule that is like this, NCO minus. Okay, how many ways can we draw the correct Lewis structure for this? So to draw the Lewis structure, we follow the same Lewis rules that we've done before. Add up the valence electrons, that's going to be 10 and 16 valence electrons, and then you write them out so that you have all of them connected in a like that. Put the least electronegative in the center, the others kind of hold hands to this least electronegative all around, and then that's 4. So that's bonding electrons, at least keeping track here. Bonding electrons, we have used 4, which means we got 12 lone pairs 12, and we are then going to put them around. So NCO, where can we put them? So here's 2, 4, 6, 2, 4, 6. That looks fine for lone pairs, but is everybody happy? Obviously not. This carbon's not, it's got just 2, 4 electrons here. So you need 4 more. You can get 2 from the oxygen, 2 from the nitrogen, or you can get 1 from here, 1 from here. Let's draw them on. We have 3 possibilities. NCO. I'm just going to do that. And over here, let's do 2 from the nitrogen, so 1 left. Or we can do 2 from the oxygen, 1 left. Or we can do 1 each. So basically moving these. So let's look at the 3 of these and see which one is going to be the best. And the way we do that is by doing formal charges. So over here, nitrogen should have 5, and you got 5 in the box, so that's going to be 0. Carbon should have 4, it's got 4 in the box, so that's 0. Oxygen's got to have 6, it's got, well, for formal charge, you only count 1 of the electrons of the bonding electrons, and all of these dots for the lone pair. So that's going to be 7. So 6 is what you should have in the periodic table, but you have 7, so it's -1. So that makes sense because you need to have a -1 on the molecule. So overall -1. Over here, oxygen should have 6. It's only got 1, 2, 3, 4, 5. So 6 minus 5 is +1. Carbon is 0, 4 minus 4. And nitrogen should have 5. It's got 1, 2, 3, 4, 5, 6, 7. So 5 minus 7 is going to be a -2. Is that even possible? Well, +1, -2, overall -1. So that is a correct Lewis structure. And what do we mean by correct Lewis structure? That means they all have octets. And so This is 2, 4, 6, 8. Now remember, for formal charge, you only count one of the electrons of the bonds to do assign the charge. But when you're doing octets, you have to count both electrons as belonging to both oxygen and carbon. So that's 2 for each bond, 2, 4, 6, and 2 for a lone pair. That's 8. And this is 8, and this is 2, 4, 6, 8. So correct Lewis structure. Charge is too high. Therefore, we can say, yes, it's a correct Lewis structure, but it is not a favored one. All right, let's look at this nitrogen. 1, 2, 3, 4, 5, 6. So 6 in the box, so that it should have 5 according to the periodic table in a neutral atom, but it has 6 here, so it's going to be 5 minus 6, that's -1. Well, overall -1. So basically, we have 3 Lewis structures and they're all correct. Let's see how we draw this and have kind of some concrete rules for drawing resonance structures. And I'm going to write this as we go along, because that way you'll understand what I mean by these rules. Actual structure has correct Lewis structures. So multiple correct Lewis structures. Now, mostly they'll have octet. Sometimes you may have a carbocation, which means you don't have an octet. So they are described by discrete bond line structures, bond line Lewis structures. So when you go between this, so we have an arrow that describes flow of electrons, describes the flow of electrons from one form, one of these Lewis structures, to another. So let's see how we can do that here. Let's say I'll redraw them. And how do we go between the two? So here's one, here's the other, and here is the other one. Now, we should always start the arrow at an electron-rich center. That means you have to start at a lone pair of an anion or a lone pair of a neutral, and if that's not possible, then from a pi bond. So the arrow must start at a lone pair, if possible, or pi bond. You should never start an arrow at a sigma bond, because sigma bonds cannot be broken. That's one of the most important rules. Sigma bonds, so the pink bonds, the first bonds here, cannot be broken, because it's not a reaction. If you break a pink bond like over here, that means you're taking this molecule and making two different molecules or atoms and molecules. That's a reaction. This is not a reaction. This is just a description. Describes. Describes. It's a description. Again, I'm just going to redraw the lone pairs over here, so we can see if we can draw the arrows and describe the flow of these electrons. It's just a potential difference that makes electrons flow between them. And let's look at these and see if you can do a flow. These start at electron rich and go to electron poor, or where electrons are needed. Over here, what's the difference between these two structures? You have three bonds here, 2 bonds. So one of them broke, and you have 1 lone pair here, and you have 1 lone pair here, and 2 here. So obviously the pi became a lone pair. So lone pairs become pi, pi's become lone pair. That's pretty much describes resonance in a nutshell. So over here, this goes over here. And over here, 3 lone pairs and 2 here. One of them disappeared, but it must have jumped in the middle because it wasn't here. So this one goes over here. Good. So that means you can go from here to here or here to here. So, and this is just a description, it's not a reaction. So we put double-ended arrows to show it's neither this nor this, it's just the electrons are in transition. Let's go over here. What happened between this and this? This bond isn't here, and you got an extra bond. This lone pair has disappeared, and obviously it has become a pi. So we cannot take, for example, this lone pair and say, oh, it went over here. You can only go to the adjacent atom, between adjacent atoms. They have to be right next door, because if you go one more, then that would be a reaction because you're going to form a new bond. So this goes over here and this goes over here, and you can see you can go back and forth. So this would be how it goes here, and if you do this and move this over here, it would go back here. So this is all in transition. So sigma bonds are never broken. Pi bonds and lone pairs kind of interchange between adjacent atoms. Now, hybridization will have to change. This is sp3, this is sp2, this is sp, you see? So it does change, and there is no rule that sp3 has to go to sp2 or sp2 has to go to sp. There's no such rule. It just depends on what happens in the molecule. Same here, sp becomes sp2, becomes sp3. Carbon, the same, sp all along. There's also no constraint that it must change. So it does, even though it looks like the hybridization changes, really this is only a description. So there really is no hybridization change overall, because it's just describing. And what is it describing? It's describing an actual molecule. And how do we know that? We know that from X-ray studies. These are just theoretical structures. They really don't exist, they're just descriptions. Descriptions of a molecule where the pi's and the lone pairs are mingling. So here it's describing this molecule. Some of the time, so you have these lone pairs here. Other than that, you have this pi bond becoming a lone pair becoming a pi, and in all of them you have a -1 charge total. So this is describing the way that electrons are flowing in the molecule. So in the real molecule, the hybridization would be closer to an sp, because it's going to be like a roll. It's going to be like in a line. So the actual molecule is closer to this. Actual molecule resembles what we call a hybrid. A hybrid of the resonance structures. And so this is the overall charge. And the hybridization in all of this would be, it will be closer to sp. So the actual molecule overall charge is a constant. That's the same as the molecular charge. So overall charge is a constant. And the charge in between here inside the molecule is just showing how electrons are shifting. So the actual structure is a sum of the resonance structures. So over here, even though we have all of this, they all are going to come together and give you the same hybridization. Now, if you take this, another important thing is that if you have second row elements or second period elements, you can have the maximum is 8 electrons per atom. You can never exceed that. Third period, you can exceed that. Third period and above, more than 8, 8 to 12. Typically 8 to 12. That's another very important point. Now, are they all the same? Is this the same as this and is this the same as this as far as contributing to the actual structure? No. So, different resonance forms may contribute different amounts to the hybrid. That's another important point. Different resonance structures or correct Lewis structures, that's what it means. Different resonance structures contribute different percentages toward the hybrid, depending on the stability. The most stable ones would contribute more. More stable would be determined by, one, is it going to have a charge on the more electronegative atom, A. 2, is the overall charge for the molecule the minimum possible. So two things basically, depending on, one, more electronegative atom has negative charge, and two, overall charge must be minimal. So here individual charges on atoms shouldn't really exceed more than +1 or -1. So if you take all these three, which one would you think is the best? Over here, according to this is the negative is on the oxygen. Over here, the negative is on the nitrogen. Over here, there's -2 here and a +1 here. So which one do you think would be the best? If I label this A, B, and C, right? If you take your electronegativity table, oxygen is the most electronegative. So over here, A has anion on most electronegative atom, which means oxygen. And overall charge is minimal, -1. It has to have a -1 because we're starting with a -1. Okay, so this could be sodium isocyanate. So over here, this is the best. Which one would be the second best? Well, over here, nitrogen has a -1, but here nitrogen is -2 and this is +1. So overall charge is also very high. I mean, individual charge is also must be minimal. So over here, overall charge would be the same, but here B would be the next. This is better than B, and that would be better than C. Here, charges too high. Charges are very high, and they're not on the most electronegative atom either. So for those purposes, A would be better than B, B would be better than C. That means the molecule, actual molecule, would have an electron density shifted more towards the oxygen than the nitrogen, because the minus is on the oxygen. That really shows a shift in the smearing is more towards the oxygen. That's what it means. Another thing is, when you're drawing these Lewis structures, you need to have as many bonds as possible and as many lone pairs as possible, and then minimum charge. One, as many bonds as possible. And once you fulfill that, then 2, as many lone pairs as possible. And how do you know how many bonds to put? You try to reach octets. What this means is, for example, if you have nitrogen, and nitrogen, that's 10 electrons, you cannot put 2 here, 8, and then say, okay, I'm going to put the rest like this, 6, or like this. 5 and 5, 10, 1, 2, 3, 4, 5. This is not a correct structure, because the rule says first try to put as many bonds as possible, then as many lone pairs as possible. So you have to put as many bonds as possible, so that's the maximum you can put. And then the rest is lone pairs. Now let's draw some organic molecules. This is just to describe it using general chemistry molecules, because that's what you're familiar with. Let's apply the same thing for organic molecules, and let's choose a very simple one. Let's say you have over here a carbon, and let's say you have a minus. A carbon minus, what does that mean? That means a formal charge of -1. That means if you have 2 hydrogens here and 2 electrons here, then carbon in this case would have 1, 2, 3, 4, 5. 4 minus 5 is a -1 charge, formal charge. Okay, so if you take this, you have over here a hydrogen, and a hydrogen. So it's always a good idea to draw them out. Now, what can we do for this? Again, this is your sigma. Sigma bonds cannot be broken, but you can move lone pairs and pi bonds. Why is that? If you draw out your sigma like this, well, your sigma is going to be along your bond. That's your sigma framework. These are just on the internuclear axis. We cannot move them because they're held tightly by the nucleus here, between the carbons and the hydrogens. These can't go anywhere. So that's why we can't break them. If you break them or move them, you're going to break the molecule. Whereas if you take the p orbitals, we talked about bonding, the 2 p orbitals coalesce to form a pi bond. Over here, you also have a p orbital that has 2 electrons. Now, in molecular orbital theory, we have these coming together and forming a bonding molecular orbital, and then we have 3 of them, and then anti-bonding molecular orbital. So therefore, we are going to have these electrons coming together and coalescing into one orbital. So pretty much if you're drawing a bonding molecular orbital for this, it's going to look like this. Like this. And then you'll have one with a node and so on. But we are not going to be able to draw these structures every single time and put bonding molecular orbital, anti-bonding molecular orbitals. So we take shortcuts by writing resonance structures for this. How can you like draw one structure for this? It's impossible because you'll have multiple molecular orbitals. So therefore, we are going to use this to draw discrete structures to describe this actual structure. And where is the anion? There's an anion, so the anion spread all over. So therefore, and it's going to be some all over here. So therefore, we have to take this and break it up into discrete structures that actually show what are the structures that contribute to this. What is the participation of these lone pairs and a pi bond to this actual structure or a hybrid structure? Okay. So here, since this is a tube, these electrons can run into each other. It's a tubular, bonding molecular orbital. And then you'll have many levels of this. I'm just only going to draw this one for right now. We can say, well, this can go in here and this can go in here. So these are actually running into each other. That's what we mean. So here's this, and the pi are interchangeable. They're in the same space. They can come back and go over here. So these really don't exist as they're drawn. They are not existing as 50% this or 50% this. There's only one structure, and this is the structure. We're just using these to describe what are the possibilities for these electrons. So basically, these electrons are like smeared on this sigma framework. So this and these two are going to be your resonance structures. Now this is a very simple one. We can kind of expand on this. For example, if you have a double bond like this, and you have a, let's say you have an oxygen like this, where should you start? First of all, draw all of your, and let's say there's a hydrogen or carbon, doesn't matter, draw all your lone pairs. I'm going to draw them in a different color because they are the ones participating. Lone pairs and pi's. Sigma cannot be broken. And here's your pi. And there are lone pairs here too. So all of the lone pairs and pi on adjacent atoms can participate. So basically, it's in this quadrant that you're going to have all of your resonance happening. Where would you start? Do you want to take a lone pair and make a pi here, or do you want to take a lone pair and make a pi here? And if you do, what are the consequences? Let's take this and move it over here. Now, if I put a arrow here, that means I'm going to make a bond here. And if I don't do anything and if I just put a bond there, look at what happens. You're going to have a bond here, and you're going to have a +1 formal charge. Is this correct? This is totally wrong because you cannot exceed 8 per second period elements. You just cannot. So this is 10 electrons, more than 8. So therefore, this is incorrect. Let's try again. Let's take this same molecule, okay? That lone pair didn't work. How about we try this one now? can I bring this over? Let's try that out. So these are just resonance, right? We're just like swishing these electrons on the sigma wire. We're not really doing any reaction. We're just trying to describe stuff to you. Let's try that. So oxygen, one of the lone pairs comes down and makes a pi bond. So well, I'm going to draw it here. Is that correct? Same problem as before. Look at that. 10 electrons. 10 electrons on carbon. That's bad. What should we do? Where should we start? So in this case, you have to start, well, you cannot do this because then we'd have to break the sigma. So this is a big no-no. This is also no because you cannot have 10. So we have to then do 2 arrows at a time. For a lot of the resonance structures, you are going to be doing 2 arrows at a time. Now, that doesn't mean 1 arrow at a time is not possible, but typically we would do 2 arrows at a time. So this is going to come over here, and this is going to go over here at the same time. It's just shifting in this direction. So then now, if you look at your resonance structure, or just the correct Lewis structure from there, you took this lone pair, made a pi. You took this pi, made a lone pair. And so basically, yeah, this is all octet, all of these are all octet structures. So this is a correct Lewis structure. So this is fine. Next thing, which is the best? Different resonance structures contribute differently. Which is the best one? Neutral structures are the best in organic molecules. Neutral structures are the best because they'll have minimal charge, basically 0 charge. Structures are best. So we are going to see which one is going to be the best structure here. So let's do formal charge to see the charge. So here 6 minus 7 is -1. This carbon is 4, so that is a 0. And over here 1, 2, 3, 4, 5, 6 minus 5 is a +1. Over here this is 0. This is 0, and 6 minus 6, 0. So you know this is your best structure, and this is a possible structure, but it is a correct Lewis structure. Now, if you did a similar thing without the hydrogen, let's say you start here and you have this structure here, and over here when the hydrogen leaves, let's say you got a anion here. You start with an anion like a acetate. This is a formate. Well, over here if you take this and do the same thing, make a pi, but in order to do the pi, something has to let go on the carbon because otherwise it's going to have 5 things to hold on to. It only has an s and a 3p. So it's got a maximum of 4 orbitals, no d orbitals there that it can reach. So it's got to pop this pi bond. So here you have the same thing, and I'm drawing all the sigma bar with the green, so we know we're not breaking those. So here you have this, and you have 1, 2, 3. So this is perfectly okay because this is octet, 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 all of them. So 2 correct Lewis structures. The very definition of a resonance, you have a -1 here, and this is 6 minus 6, 0 and 0. And over here this is 0 and -1 here and a 0. So overall -1 charge is maintained. All right, so do we have a better structure here? Let's look at it. -1 on the oxygen, -1 on the oxygen here, 0, 0, 0, 0. They're both the same. So they're contributing 50% here and 50% to the resonance. Over here, this might be contributing like 90-some%, and this might be contributing less than 10%. So mostly over here. I know this is not conventional, but it's mostly on this side. That's where the resonance is. And this is maybe a little flash over here, but for the most part, the electrons are here. Just a little bit over here. But here, they are going to be flowing very nicely between the two. So in summary, we just want to go over the rules with you. Resonance is a description of an actual molecule, a molecule that exists in physical space using many multiple correct Lewis structures. We're just describing an actual molecule with molecules that actually do not exist, but they can contribute to the knowledge of this structure. Now, when you have lots of pi bonds like this, the pi bonds can come together and coalesce a molecular wire. According to molecular orbital theory, they can all combine, linear combination of atomic orbitals, so they can combine, which means electrons can be anywhere here in these orbitals. So therefore, when you draw these electrons like this, they're really not correct, okay, these structures, because they can be anywhere in this region, on top or bottom. So this is just a representation of possible locations for these lone pairs and pi's, or anions and pi's. So you have these electrons that can actually travel in the molecule. It's like a molecular wire. And you see that in LCD panels and so on. It's nothing but just electron wires, electrons delocalizing along a sigma framework from end to end. So one of the things that are really important for you to bear in mind, you cannot break sigma bonds. Overall charge is a constant. If you start with a -1, every single structure is a -1. And another one is the second period elements, maximum 8. You cannot exceed 8. You cannot make bad structures like this. That's really important, and that comes with practice. So electrons can go from lone pair to pi, pi to lone pair, pi to pi. So you can see this is going from lone pair to pi, and pi to lone pair. You really have to make sure that you know that they only go between adjacent atoms. So the resultant structure, the hybrid, is a sum of the individual structures, and each of them contribute towards their actual structure in different amounts. Things that have negative charge on more electronegative atoms are better than things that have, let's say, a positive on electronegative atoms. Things that have +1, -1 are better than things that have like +2, -2. So minimal charge is better. The best structure would be where everything is neutral and in resonance, but you don't always see that. So minimal charge is the best. And then you need to have as many bonds as possible and lone pairs as possible, and then you should have the minimal charge possible. We're going to come back and do a lot more practice for resonance. Bye.